This is just a practice version of your common assessment. So not every class, but several classes you've probably taken have had common assessments. This is just another one. So all math 14 classes get the same common assessment. And what we have here is just a quadratics problem. So we'll work on this piece by piece. Okay, so what we have here is the scenario that we have at the top. And all it's saying here is that we have the height of a ball is thrown from the ground. So like we assume it's sitting on the ground, we throw it. It's thrown from the ground with an initial velocity of 32 feet per second and can be modeled by the equation h of t is equal to negative 16t squared plus 32t, where t is your time in seconds after the ball is thrown. Okay, so my very first question is we want to calculate the time it takes for the ball to reach a maximum height. So we need the time it takes to reach this maximum height and determine the maximum height that it reached. So when you see maximum or minimum, when we see those terms, we know that what we're looking for is a vertex. So we know that what our vertex is that the vertex, the first point is just going to be negative b over 2a. And the second component is that you just feed it back into the function. So our function is not f, it's going to be h. So we just feed that x component back in to get the y component. We have h of t is equal to negative 16t squared plus 32t. And we're used to looking at something that looks like ax squared plus bx plus c. Well, there's a c, it's just 0 in this case. But what we see here is that the a always goes on the squared variable, so it's going to be negative 16. B is on the unsquared variable, so that's going to be the 32. And we don't need c because we just need a and b for vertex. So when I look for my vertex, so remember, we used to call this h and k. So the time part of that, because we're using at time and h of time, we don't have x and y here, we have variables t and h of t. So the time is just going to be the negative b over 2a, or in this case, the negative b is 32 divided by 2 times a, which is negative 16. This is just going to be negative of 32 over negative 32, or negative negative 1, which turns into positive 1. So time is just going to be 1 second. So it just takes me 1 second to reach max height. Now, if we want the other part of it, we want the height, that's h of t. So we know what t is, so RT is going to be 1 times 1. But when is that? What is that maximum height at 1? Well, that's just going to be negative 16, 1 squared plus 32 times 1 plus, oh, we don't need that plus 0. We're just looking at this form up here. So I just replaced all my t's with a 1. So I'm just going to get negative 16 plus 32. So I just get 16, and that should be feet. My maximum height is 16 feet. Okay. So let me pause this, and we'll just put in a more blanket statement here, and then we'll move on to B. So we can just rewrite this as the ball reaches a maximum height at 1 second after throwing, and the maximum height is going to be 16 feet. Now the next part highlight what we're looking for here again. So here we want to find the times when the ball is at ground level. And we want to know how long does the ball stay in the air. So if you think, what is ground level? That means my height is 0. So I'm looking for when h of t equals 0, when my height is 0. So when we have this problem here, we're sending the quadratic to 0. What we're looking for is zeros of the quadratic, or you're looking for x-intercepts. So we have this problem now. We have we had h of t is negative 16t squared plus 32t. But now we have 0 is equal to negative 16t squared plus 32t. So we got a quadratic equal to 0. We can solve this with some factoring. Both 16 and 32, you can factor out a 16 from, and then we have a t and a t, so I can factor out a negative 16t, leaving behind a t minus 2. So that's the factored form. So either negative 16t equals 0 or t minus 2 equals 0. So what we get here is either t is 0 or t is 2. So the ball, when it is ground level, is going to be at 0 and 2 seconds. So how long was the ball in the air? Well, I threw it up at 0 seconds and it came back down at 2 seconds, so 2 seconds. So we can just say that the ball is at ground level at 0 seconds and 2 seconds. The ball is in the air for 2 seconds. So part C, we want to sketch the graph of the quadratic function and label the intercepts and vertex. So we already found all this information. So remember, this is my equation. And we already, in part A, we found a vertex, right? And what we found was that the vertex was going to be at 116. So at 1 second, it reached 16 feet. Part B, that was my zeros, or x-intercepts. So we had those at e equals 0 and 2. So we want to label vertex and intercept. So we really don't need a y-intercept. I know you're asked for intercepts because we already have an x-intercept at 0, but if you did your y-intercept, just remember that is when our independent variables, in this case, t would be equal to 0. So you get negative 16, 0 squared plus 32 times 0, which would just give you 0. So you do have a y-intercept at 0. Like I said, we just don't really need that because we have the x-intercept at 0. So I'm 0 at here and here. And let me see, 10, 11, 12, 13, 14. Okay, it's counting by twos. So this is 12, 14, 16, 18. Okay, so this is my 16 right here. This is 1 and 16. All right, and I'll just as smoothly as possible. So we know my writing pad doesn't make this easy to do. Here, so something kind of like that. So you expect a parabolic shape. Okay, so let me scroll down, pause this, scroll down, and then we're going to do the remaining parts of this question. So next we're going to use the graph to describe the motion of the ball. Then we want to provide real world examples that can be modeled using quadratic equations. So how we can describe this? Oops. Let's look at this nicer little version of it. Just a second here. All right, I got something popping up. There we go. Just trying to get my tool to come up here and it's just not coming up. So how we describe this? So technically this is going below the x-axis here and here. So the negative parts of the graph are unimportant. So they're not important because we can't be below 0 feet. If we did, that means that ball is driving into the ground. We cannot have a height less than 0 feet. That doesn't make sense. So that is one problem that we have. You could describe this as we start at 0 and the ball rises. Times 0 when the ball is on the ground. And the height rises or increases until 1 second after throwing. It reaches a maximum height of 16 feet. Then the ball falls until it hits the ground at 2 seconds. And it's 2 seconds from throwing. Last little bit here, so we just want to provide some real world examples that can be modeled using a quadratic function. So you can kind of think about anything that's being thrown. So any kind of situations where we're throwing something up and it's coming down. Like throwing a basketball. I mean, it's not going into a hoop. If we throw it up, it's going to go up, arch, and come back down. Anything that we do with projectiles, or you can think of missiles. There's other situations that we have because sometimes there is like functions that we look at that are trying to find maximum profit. So sometimes maximum profit functions will also have the same shape. It would be something that we can use it as a quadratic function.